Hi students, Professor Nugent here. In the last video, we just concluded that general least squares estimators are the best linear unbiased estimators of beta j. They're more efficient than OLS estimators. Now we just brought in this term, generalized least squares estimators. What are these things? Well, the generalized least squares estimators for correcting heteroscedasticity are the weighted least squares estimators. So let's specify what these generalized least squares estimators actually are, and we're going to show that the weighted least squares estimators are a special case of generalized least squares estimators that give us the best linear unbiased estimator of beta j in the case that we have heteroscedasticity and we know and can specify the functional form of that heteroscedasticity. So these estimators are the values of Bj that minimize the following: the sum from I equals 1 to n of yi minus b0 minus b1 x1I all the way through bk xki squared divided by hi. So you see, we're minimizing the sum of squared residuals where that squared residual is weighted by the inverse function of h. And we can transform this by bringing h inside this function, so that if we have a sum from I equals 1 to n, we can write it like this: yi minus b0 minus b1 x1I all the way through bk xki the same thing: yi minus b0 minus b1 x1I all the way through bk xki this is over square root hi over square root of hi. So square root of hi times square root of hi. You have two different terms here. You can bring the hi into this term so that we have a sum from I equals 1 to n yi over square root hi minus v0 over square root hi minus b1 x1I over square root hi all the way through bk times xk over square root hi times the same thing, so this is just squared. And now we can rewrite this as a sum from y equals 1 to n of yi squared, yi star minus b0 x0 I star, where x0 I star is 1 over the square root of hi minus b1 x1 I star minus all the way through bk xk I star squared. So this looks a lot like OLS, right? So the weighted least squares solution here can be seen as OLS on the transformed variables, because OLS solves the objective function that minimizes the sum of squared residuals, which is what we're doing here, only we have transformed variables, right? So we have transformed all of these variables to be divided by 1 over the square root of hi, where hi is that that function of the variance. So Stata can help with this. Stata has a WLS estimation command where we just specify the weighting function 1 over hi, so that the weights are proportional to the inverse of the variance. Now when we have an estimation, this estimation method as we have expressed above, then the interpretation of the standard errors, the estimates, the beta j hat, the test statistics, it's all the same. And when I say the same, I mean it's all in the context of the original untransformed model. So we're thinking about data that is not transformed. So you interpret the coefficient as it relates to data that is not transformed. From the WLS package, you may get an r squared, which is not useful because this r squared is explaining variation in y star, and that's not the explained variation in which we are interested. If we are using firm level or population level averages as our smallest unit of measurement in our regressions, and we can assume the individual level individual level regression demonstrates homoscedasticity, then the weight in this case may be the size of the firm or the size of the population. If we cannot assume the individual level regression demonstrates homoscedasticity, so when we say individual level, we're thinking in the case of the firm, the individual worker level regression. If in that case individual level demonstrates heteroscedasticity, or we don't know if the individual level demonstrates homoscedasticity, then what we can do is two things. Use WLS for the firm level or population level average function, and then two, use heteroscedasticity robust standard errors.